Okay, welcome to chapter 7, and today we begin our understanding of trigonometry. So our next 3 or 4 chapters will all be trigonometry, and that's the last major standard trigonometry that you need for going into calculus. So this is really, really important stuff. I think you're going to find this stuff pretty easy, honestly. I've been teaching trig for a long, long time. And you guys are going to love it. So take great notes, ask questions, do your homework carefully, get help when you need it. You're going to do great. So 7.1, we begin our study with trigonometry just to study the measurement of angles. All right, and so we have to understand the definition of an angle. And I know you know what an angle is, but we're going to take it farther. We're going to talk about the parts of an angle and different ways to measure angles and things like here. Well, let's read the objective. To find the measure of an angle in either degrees, which you've been working on with most of the time, or radians, and to find coterminal angles. So radians may be new to a few of you, the radian measure of an angle, and coterminal angles would probably be new to a few of you. All right, so we're going to begin to develop our understanding of these today. So first, there's a great picture of an angle that I'd like you to draw into your notebook right here. And let's talk about the parts of an angle. An angle, which I never write the word angle, I just do the angle symbol, represents a rotation about a point. All right, so you see the point P, all right, and the angle theta right there. We're rotating what we call an initial ray about point P, theta degrees or radians to get to our terminal ray. Well, let's get all that written down. So the angle shown is the result of rotating its initial ray, so here's the initial ray, to its terminal ray. And to rotate an initial ray to a terminal ray, we have to have a point that we're going to rotate about and an angle measure right there. And that will lead this initial A to be rotated to our terminal ray right here. Okay, now let's think about, where did angle measure come from? Let's talk degrees first. There are blank degrees in 1 revolution. All right, well, now 1 revolution, think about basketball. It's all-star weekend, slam dunk competitions. Remember the 360 degree slam dunk? That is 1 revolution right there. So 1 revolution is 360 degrees. All right, how do you think the Babylonians came up with that measure for 1 revolution? All right, well, you notice within the circle we've inscribed, 6 equilateral triangles? The Babylonians subdivided the angles of an equilateral triangle into 60 equal parts called degrees. So these are all equilateral triangles and they're all congruent. That means that each angle of an equilateral triangle, which you already know this, would be 60 degrees. 60 degrees and 60 degrees. Let me take a time out. I have a dog that wants out of the office. Roxy, do you want outside? Go ahead. Go. It's tough when I share my office with my dog. All right, now these are all congruent equilateral triangles. That means 60 degrees right here. Wouldn't I have another 60 degree angle right there, and so on? So since 6 equilateral triangles are arranged within a circle, 1 revolution contains 6 times 60. There they are. Or 360 degrees. And that's how we came up with 1 revolution is 360 degrees right there. Angles can be measured more precisely by dividing 1 degree into 60 minutes and dividing 1 minute into 60 seconds. All right, and you'll see this kind of measurement on property stakes if you ever go look at a piece of property. So this is an angle that is 25 degrees, 20 minutes, and 6 seconds. Wow. So again, one more time. 25 degrees, 20 minutes, and then 6 seconds. And there you go. A much more precise measurement right there. So 12.3 degrees. One of your jobs will be to convert angle approximations to degrees, minutes, and seconds. So we're going to start with this. The decimal approximation to degrees and minutes. So we want to take this angle that is 12.3 degrees and write it in degrees and minutes. It's just arithmetic. All right? 0.3 degrees. Well, let's think about that. 0.3 degrees, wouldn't that be 3/10 of 1 degree? 3/10 of 1 degree, or 0.3 or 3/10 of, and how many minutes are in 1 degree? 60. All right, so what is 12.3 degrees then? Well, it would be 12 degrees. And then what's 3/10 of 60? Well, 10 goes into 66 times, and 6 times 3 is 18. So that would be 12 degrees and 18 minutes. There you go. Okay, hey, look at this one. Now we're going to go 25 degrees and 20 minutes and 6 seconds. We're going to do the decimal approximation of that angle. Degrees, minutes, and seconds to a decimal approximation. So 25 degrees plus 20 seconds. And let's think about that. 20 seconds, wouldn't that be a fraction of a degree? And that fraction would be 20 over, and how many minutes are in 1 degree? 60. So that's 20/60th of 1 degree. Plus, and now we're in seconds. So this is going to be 6. And now think about that. There are 60 minutes in 1 degree, and there are 60 seconds in 1 minute. Therefore, there would be 3,600 seconds in 1 degree. So that's 6 over 3,600. And now you just punch this out on your calculator. Equals, all right, here we go. So I have 25 plus 20 divided by 60 plus 6 divided by 3,600. Double check. That looks all in there correct. And I'm getting 25.335 degrees. 0.335 degrees. And that's exact, by the way, too. Nice. Okay, now let's talk about arc length. Arc length. Well, you see a circle on your slide here. And what's an arc length? Let's visualize it first. You know what an arc is. All right. This is arc AB right here. An arc is a fraction of the circumference of a circle. And it's actually gives what's the distance from point A to point B. That would be arc length. Okay. Now, arc length always equals, and this is where radian measure came from, by the way. All right. Arc length equal to the radius. So let's picture the center of the circle and then do 2 radii from the center of the circle, one to point A and one to point B. So point O is the center of my circle, and there's one radius from the center to point A, and the radius there from the center to point B. Okay, now this arc length right here, that means that the distance from point A to point B is exactly r units. Okay, so the measure of angle AOB, and remember how you do angle measure here, O is the vertex of that angle, so you have to call that angle AOB or angle BOA. The order doesn't matter as long as your O is in the middle, the vertex of the angle. Okay, so there's the angle right there. All right, now what is that angle approximately in degrees? And you guys would probably look at that and say, I don't know, that's about a 60-degree angle. Guess what? That angle is approximately 57 degrees. So if you said 60, awesome. Now, let's go somewhere else here. the measure of angle AOB equals 1. Well, that doesn't look like 1 degree, but might it be 1 radian? 1 radian. And that means this intercepted arc right here is exactly the distance of the radius of the circle to create that angle of 1 radian. So arc length will always equal, and we use an S for the arc length, will always equal my angle measure of the central angle, theta, times the radius of the circle r. And there's your first formula for arc length right there. All right. Now this works when our angle is in radians. All right. So you've got to be in radian mode if they ask you for the arc length, and you know the radius of the circle and the central angle of the circle in radians. Okay. Now, so arc length S equals theta times r. So this one, the theta is 1, and the radius is r. So again, this is an arc length of r units, and this angle has a measure of r radians right there. So, oh, look at this one. Oh, well, what do you think that angle might be? I don't know. And remember now, let's do it again. Arc length S equals theta times r. All right. So the measure of angle AOB, well, I don't know, that's approximately, that looks a little less than 90 degrees to me. So I called it 86 degrees right here. Now let's check it out right there. Okay, the radius of the circle is 1. All right, what are we going to do? Okay, 1.5. So that tells me that this angle right here creates an arc length that is 1.5 radians right there. Because again, arc length equals what? S equals theta times r. And the radius is 1. So that would make this 1.5 radians. There you go. Or approximately 86 degrees. Okay, so S equals, one more time, theta times r, 1.5, and that's units. And don't confuse that now. The angle is measured in radians, all right? The arc length is a distance measured in units. Okay, oh, hey, one more. You guys want to approximate this one too? So, angle theta right there. Well, the number of radius units in the length of arc AB. So how many radii do I have if I travel from A to B? Well, it looks like more than one of them right there. All right, how many? Arc length S. S equals theta times r. Okay, so radian measure of the central angle, angle AOB. All right, so that implies, well, what would theta then equal? Well, let's take this little formula we have up here and let's solve for the angle theta. And that would be theta equals S divided by the r, arc length over the radius. Let's write that out in words. So a central angle theta in radians will always equal the arc length of the circle over the radius of the circle. There you go. Take this all in. I feel like I'm going a little fast here. If I am, I apologize. I'll try to slow down. Okay, so how many radians correspond to one revolution? Well, we know one revolution is 360 degrees. How many radians would that be? Let's think about this. One revolution, okay? 360 degrees. What is that in radians? Well, theta equals, and what did we just said? Theta is arc length S over the radius, right? So I think we can figure this out pretty easily here. That would equal then, well, one complete revolution. So picture a point right here, and let's go all the way around. The complete arc length of a circle. Isn't that the circumference of a circle? And isn't circumference of a circle 2 times pi times the radius? So if I take 2 pi r and I divide it by r, my r's cancel, and this angle theta is 2 pi. There you go. That would be 2 pi radians right there. So 360 degrees then would have to equal 2 pi radians, which means, well, let's divide both sides by 2. 180 degrees would be pi radians. Okay? We're starting to get a feel for this now. Okay? I hope you can picture a little better. So 1 revolution would be 2 pi. 1/2 of a revolution would be pi. How about a quarter revolution? Pi over 2? You betcha. Get a feel for that. Okay, so we have conversion formulas which will lead to the easiest problems you do in trigonometry. All right, it's pretty simple. 1 radian equals what fraction of a degree? Well, we're developing unit multipliers right here. And do you see this statement that we just made? 180 degrees equals pi radians. So 1 radian, let's just divide both sides by pi. So 1 radian equals 180 over pi degrees. Okay? Now, just in case you're curious, and you don't have to have this memorized, believe me, let's punch out 180 divided by pi. 180 divided by second pi. And I'm getting 57.30 approximately. I'm probably going to take this a little longer here. 57.2958 degrees. All right? So 1 radian is really approximately 57 degrees. You remember we showed that in one of our earlier slides? All right? Now, 1 degree, well, we can go the other way here. Equals what fraction of radians here? Well, see this 180 degrees over pi, which equals 1, by the way. All right, how about if we go pi over 180? There you go. And that would be 1 degree is pi over 180 radians. So let's punch that one out. Second pi divided by 180. And I'm getting, 0.0174532925. Wow. How about 0.01745333? Let me see. Yeah. Okay, and I rounded that there to that 3. And I'm not even going to tell you what place that is. Okay, good. So, just in case you're curious, all right, do not try to memorize these. Okay, so here's what this is used for, though. Convert 196 degrees to radians and round to the nearest hundredth. Yeah, that's kind of ugly right there. All right, so all you do is you take your 196 degrees and you multiply it by 1. But your 1 will look like this. All right, now let me see. You want your answer in radians, so you want a factor of pi in the numerator over 180 degrees in your divisor, just like that. Now look what happens right here. The measurement of degrees would cancel out, and all you have to do is punch out 196 times pi divided by 180, and you've made your conversion. So that is approximately, so let's punch this out carefully. Clear. 196 times second pi divided by 180. And I'm getting, and what do they want to round to? The nearest hundredth. So I'm getting 3.42. And that's 3.42 what? We're going degrees to radians, so that's 3.42 radians right there. Beautiful. Now we can convert the other way too. Let's convert 1.35 radians to degrees. And we're going to do this one to the nearest minute, right on. So let's just go 1.35 times. And now we're going to multiply this by 1, but that 1's going to be written as a fraction. And now I want my answer in degrees, so I'm going to go 180 degrees in my numerator over pi in my divisor. Now let's punch that one out. So 1.35 times 180 divided by second pi. Boy, it's been a long time since I hit pi on my calculator. Where is it? There it is. Okay. And I am getting 77. And what do they want to the nearest minute? Well, I'll do this as a decimal approximation first. So I'm going 77.35 right there. And now I've got to convert this decimal approximation to degrees and minutes. So that's 77.35 degrees. So to the nearest minute, that would equal 77 plus, and then I've got 0.35 of, and one more time, how many minutes are in 1 degree? That would be a 60 right there. Now let's punch this one out. 77 plus 0.35 times 60. All right, and I'm getting 98 right there. So let's think about this a second, and I blew that here. I need this to the nearest tenth of a minute, so I shouldn't have punched it out like that. I should have gone 77 degrees, and then punched this part out and round it to the nearest minute. Okay, so let's try that. 0.35 times 60, and I'm getting a 21 right there. 21 minutes. So 77 degrees and 21 minutes. Beautiful. Okay, so again, make sure you can convert degrees to radians, and make sure you can convert radians to degrees. Okay, now angles whose measures are multiples of pi over 4, pi over 3, and pi over 6 appear often in trigonometry. These are our key angles in the first quadrant right there. The diagrams below will help you keep the degree conversions of these special angles in mind. All right, so some special diagrams that I want you to write down. I think I might even be giving you a copy of these today. Okay, pi over 4. Well, picture pi over 4 right now. Pi over 4, I want you to be thinking pi over 4 is equivalent to 45 degrees. So there it is right there. Pi over 4 is 45 degrees. And these are all multiples of pi over 4. Pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 0. That's the radian measure. Then inside you have the degree measure of each of those. 0 degrees, 45 degrees, 90 degrees, 135 degrees, and so on. All right. These are key angles in trigonometry. All right. Now I'm going to give you another diagram with the multiples of pi over 3. And pi over 3, all right, that's 60 degrees. So there it is right there. So pi over 3 is 60 degrees. And then you have your 2 pi over 3. And then 3 pi over 3, which is pi. And then 4 pi over 3. And then 5 pi over 3, and then 6 pi over 3, which would be 2 pi, and you're back at 0. Those are your radians, and your corresponding degrees would be 60 degrees, 120 degrees, 180 degrees, 240 degrees, and 300 degrees. Be able to convert these key angles from radians to degrees or vice versa automatically. You shouldn't have to use the conversion formulas. You could, it would work, but it would just take more time. And now, pi over 6. Pi over 6 radians is equivalent to 30 degrees. And I'm not going to do all of the multiples of 30 degrees because some of them have already been represented in the previous two. But here's some key ones here. Pi over 6, and then 5 pi over 6, 7 pi over 6, and 11 pi over 6 right there. All right, and pi over 6 is 30 degrees. 5 pi over 6 is 150 degrees. 7 pi over 6 is 210 degrees, and 11 pi over 6 is 330 degrees. All right, there's your key diagrams, and I'm going to give you a copy of that. At least when we're remote, I will give you a link so you can print out a copy of this. Okay, standard position of a positive angle. All right, well, note we have the coordinate plane right here, actually. All right, and the origin will be the vertex of an angle in standard position, and the initial ray will be on the positive x-axis right here. So that would be the standard position of a positive angle, and whatever that measure is right there, all right, that would be the measure of that angle. Initial ray and the quadrant 1 terminal ray right there. All right. Whoa, look at this. Oh, I see where we're going to go. We're going to go coterminal angles. Well, what would this measure be? Well, you know 1 revolution is 360 degrees, and that's a little farther than 360. I don't know, I'd approximate that about 20 degrees. So let's see. Just approximating here. 360 plus 20 more, do you think that might be 380 degrees? Haha, look at us. There we go. All right. So 380 degrees right there. All right. Now, watch this. This is called a first quadrant angle because the terminal ray is in the first quadrant. Okay. And by the way, that is a first quadrant angle of 20 degrees right there. All right. And 20 degrees and 380 degrees are called coterminal angles. They are 2 different angles that have the same terminal ray. All right. I'll look at this one. All right. Now this angle, by the way, notice on the last slide, an angle in a positive direction is rotating counterclockwise. So this angle would be rotating my initial ray to my terminal ray, and that's going to rotate clockwise. So this is a negative angle right there. All right. Initial ray, terminal ray. What do you guys think that angle might be right there? All right. And hey, let's try this. It looks like negative 90 degrees, but what would that be in radians? That's right. Negative pi over 2 radians. Pi over 2. And if you have an angle in terms of pi or a decimal approximation, it is assumed to be in radians. You don't have to write radians every time. But if your angle is in degrees, you have to write that degree symbol. And this is called a quadrantal angle because the terminal ray is on one of the axes, unlike that first quadrant angle we saw on the last slide. All right, a quadrantal angle has a terminal ray on one of the axes. All right, and the initial ray again is always the positive x-axis. Okay, coterminal angles. Well, we just verbalized that a second ago, but here we go. Implies 2 angles in standard position that have the same terminal ray. Any given angle has infinitely many coterminal angles. Wow. And we saw that a second ago when we had the 380 degrees has the same terminal array as the 20 degree angle did, and we could keep doing revolution after revolution after revolution infinitely many times. And you know what? We can go either direction too, positive or negative. So here we go. This angle right there, I don't know, let's approximate that. And let's start working on radians. That looks like, well, let's talk degrees first because you're comfortable. Is that about 45 degrees? Pi over 4 radians. Right on. Okay. Oh, so what's this one going to be? Well, remember, 1 revolution in radians would be 2 pi plus pi over 4 more. So I'd go 2 pi would be 8 pi over 4 plus pi over 4. That angle right there is 9 pi over 4. All right? And 9 pi over 4 radians and pi over 4 radians are coterminal angles. They have the same terminal ray right there. We could also go negative. That one right there. All right? Well, that's negative because it's going clockwise. And if it went all the way around, it'd be 2 pi, but we're pi over 4 short of that 2 pi. So that would be 2 pi again is, 8 pi over 4 minus pi over 4? That'd be 7 pi over 4. Negative 7 pi over 4. Don't forget your negative there. Again, there we go. So these are 3 coterminal angles. Now, if I remember test questions, they usually do something like this. Give 2 coterminal angles of the angle pi over 4. Make sure one of them is positive and one of them is negative. Great test question right there. Okay, your homework then is page 260. I want you to do the class exercises 1, 3, and 5. And then the written exercises, all I want you to do is 11B, 13B, 21, and 23. And you guys notice that I have most of those problems written in red. That's to tell you that those problems are formatted exactly like test questions. By the way, 23 doesn't make that any less important as part of your learning, so make sure you guys do that. 1, 2. Have a great day, and give me an email if you have any questions on this stuff, and have fun.